Another thing that comes up sometimes on problems is when you have systems of objects where there's more than one and they're linked together in some fashion. So this is a really classic example where you've got the green block that's on top of the table and you've got a red block that's hanging and they're connected by a string over this pulley. So the red block has a force of gravity pulling down on it, and it's going to pull the green block along with it. And we want to figure out both the acceleration of the system, the acceleration of both of these objects, and we want to know the tension in the rope. This is actually not nearly as hard as the block on a ramp because we have a really powerful trick here. Now, before we begin, it's always a good idea to just look at it and sometimes use your common sense, as you probably knew what would happen before you even started taking physics, which is just the red one's going to pull the green one down. But what's very interesting to note is that they're going to go down together. Their destinies are linked. Wherever the red block goes, if the red block ends up dropping by 2 meters, then the green block is going to get pulled 2 meters. The fact that they're connected by this rope simply means that their motion is going to be the same as long as there remains tension in the rope. And we can really take advantage of that here. So what I'm going to do in this case is make an unusual type of force diagram. I'm going to make a force diagram of forces on the entire system. Forces that are pulling this whole set, these two blocks, and trying to move them somewhere. And the way that you set that up is a little different because there's really only two types of forces. There's forces that are telling everything to go this way, and there's forces telling everything to go that way. And I'm going to list them out. So if I draw this whole thing and I look at the forces that are pushing the entire system in this direction, there's a downward force of gravity of 20 newtons coming from this block that's trying to pull everything that way. And in this direction, well, there's no friction on it, so there's actually no forces that are stopping the red block from moving this thing. And that's why it's going to accelerate, because there's a net force here. So we can actually determine that the net force on the system is 20 newtons. Now, once we know the net force, the next step is always going to be running Newton's second law, F net equals ma. But in this case, what mass do we use? Well, those 20 newtons of force aren't just pulling the red one anymore. It has to drag the green block along with it. So in this case, the way that we have to plug it in is going to be, for the net force we've got 20 is equal to 8 times A. Because you have to look at it. You have 8 total kilograms that are being moved by those 20 newtons of force. So you end up with an acceleration of 2.5 meters per second for the entire system. Even though the green one isn't pulling on the red one to stop it, just the fact that it has mass means there's more stuff that's got to be pulled. So it's not going to fall at 9.8, it's going to fall at much less than that, 2.5 meters per second. Now the second part of the problem is a little trickier. It asks, what is the tension in the rope? But the problem is, since we treated this as one object, we basically ignored tension, which was nice because dealing with the force of tension would have been tricky. But now we've got to kind of handle it. So the way that we do that is we're no longer going to look at it as one object anymore. We're now going to treat this as two objects again. We're going to treat it as the green block and the red block. So let me draw the separate force diagrams, which now will include the force of tension. Now, if I draw separate force diagrams for each one, you end up with, on the green one, a downward force of gravity of 60, and a normal force of 60, and a force of tension that we don't know. And on the red one, you get a downward force of gravity of 20, and an upward force of tension that we don't know. But there's a really important cool fact here, and that's that the force of tension is going to be the same for both of these because it's the same rope that they're sharing. And we also have to our advantage the fact that we know what the acceleration is. Both of these blocks will have an acceleration of 2.5. If I take advantage of that information for the green block, then I get a net force of 15 newtons. And since that net force is coming from the force of tension, then I find out that the force of tension is equal to 15 newtons. But I just said a second ago that we should get the same force of tension on the red block. So let's give that a try and hopefully they'll match up. When I work it out for the red block, I end up with a net force of 5 newtons. Wait, that's not 15. Oh, but it wasn't asking about the net force. It was asking about the force of tension. So check it out. If the force of gravity is 20 and the net force is 5, then the force of tension is 15 newtons. And we get the same thing over here for each of them. So as a quick recap of what we did, we treated the two objects as one. And when we did that, we could draw a force diagram for the entire thing. Once we did that, we found the acceleration. And using that information, we were allowed to draw force diagrams one at a time, and we could take advantage of F net equals ma to find the missing forces and to get that final force of tension.